Okay, cool. Welcome to day 2 of programming module. Today we will be covering what machine learning actually means, and then we'll go into linear regression to see how exactly it works, so that in the next sessions we'll build up to our project. So here I have my presentation open. So machine learning is how exactly is it different from a traditional program? In a traditional program, what you do is you give the computer a specific set of steps that it has to follow to get the task done. Meanwhile, in machine learning, what we do is we build a model, and we like each class of task has a different model that we could use, has different models we could use. What we do is we build a model and we let the computer figure out what exactly it has to do. For example, say I need to split the real line into positive numbers and negative numbers. So what I will do is I will write a code saying if x is greater than 0, then positive. If x is lesser than 0, then negative. But if we are to do this very simple task, this seems very redundant, but we'll see that when tasks become complex, machine learning becomes very useful. So what I will do if I am going to implement the same thing in machine learning is I will tell the computer, okay, classify the data I give you into 2 classifications. And I will give the computer a lot of data. And this is an example of supervised learning. I'll give the computer a lot of data and ask it to learn from it. So I'll tell the computer, okay, this belongs to positive class. This belongs to negative class. And then the computer will develop some sense of which all are positive and which all are negative, and it will do the task. Formally, a computer program is set to learn from experience E, which is the data set I gave here, with respect to some class of task T, which is the classification we're doing here. And performance is measured as P. If it's oh wait, I have repeated it. But anyways, so you have E, T, and P. And we have to correct this in the PPT. So we have E, T, and P. What a machine learning program does is using E, it'll get the tasks T done, and P will be the measure of how good it is. For example, it could be accuracy, 90% accuracy, 95%, or actually 95% is very good. If you aim at 80%, then that's P. The experience is the training data set here, and the task is your test data set or your whatever classification. So machine learning algorithms are majorly divided into 2 types: supervised learning and unsupervised learning. We'll come back to that. So supervised learning is when you give the machine a training data and let the machine learn from the data first, gain experience from that data first, and then apply it to tasks. In our example, what we used was supervised learning. What we did was we took the data, we told the machine this is positive, this is negative. So that is supervised learning. And note here that in this type of learning, we have to prepare the data. Supervised learning, the major 2 types of supervised learning we have are classification and regression. Classification is the example we just saw. So one example algorithm for classification is decision tree classification. You can learn upon it later if you want. We won't go into that. And regression is when the machine is supposed to predict a continuous type of thing. For example, say you have some data on, okay, you probably did this in school. You plotted some experimental data, and then you want to fit a line to that data. And using this line, you want to predict what the next data point would be. For example, say you're measuring current through a circuit, given the voltage. So you would plot current in the x-axis, voltage in the x-axis and current in the y-axis. And then you'll probably draw a line. The line wouldn't pass through all points, but it will be the best fit you could come with. And say your teacher asks you to predict the current for a higher voltage than whatever you were given. Then you would probably pick the point on the line that corresponds to that x value, and then tell your teacher that this is the current. That is exactly what linear regression is. And this kind of fitting a curve is called regression. So these are the major two types of supervised learning tasks that we usually deal with in machine learning. And then we have unsupervised. In this, what we don't have is the training set. We do not really label a set of data and then give it to the machine. What the machine does is it gains experience from the same data set, and it will perform on the same data set. So this might be confusing at first, but let's see one example. Look at, okay, we'll deal with the clustering example. Look at this screenshot. Does anybody have a question? Okay, it's Prakar. So we have, look at this screenshot. So we have a lot of random points on the Cartesian plane. Now, if you ask some of your friends to group this in two, what they would probably do is they'll pick one chunk and call it group A. They'll pick one chunk and call it group B. And how we do it, we visually see where it's very dense and call that one group. This is exactly what a clustering algorithm will do. It'll group things, basically. So in this, now you kind of get why we don't need to train the program, right? Because if you look at it, you can say that, okay, this part is dense, so this should be one group. This part is dense, so this should be another group. That's exactly what unsupervised learning does. It just looks at the data and figures out what to do. It doesn't have a training phase to it. And we don't need to prepare a data set for this kind of a machine learning program. And we have another kind of unsupervised learning task, which is association. We also call this shopping bag analysis or something like that. I'll tell you what it is. So, for example, say somebody buys bread always when they buy jam. Not somebody, but let's say that's a popular trend to buy bread always when you buy jam. And they also buy milk, but that need not have any correlation with buying bread or jam. So we give this kind of a data to the machine. So what the machine will tell you is exactly whatever I told you just now. It'll tell you, okay, people seem to buy bread along with jam, and people don't seem to buy milk along with bread, or I mean, there's no correlation. And maybe there's also something else the machine notices. The machine probably notices that people who buy orange flavored jam don't buy strawberry flavored or whatever. So this is exactly what association is. Again, here you don't need to train the machine. You just give it a data set. Like a data set is probably person A buys this, person B buys this, person C buys this. So what the machine does is it reads through the data set, and then it realizes, okay, these people seem to buy these two together, and these people seem to not buy these together, and these two things don't seem to have any correlation or whatever. That's exactly what an association task is. Now I hope I made it clear what supervised and unsupervised are. If you have any doubts until here, you can ask them right now. Okay, cool. I'm assuming we don't have any doubts. So we'll move on to linear regression. So until here, we just saw things in a very theoretical way, in a very, at least when I was learning, I couldn't get a grasp of what is going on until I implemented something. So that's what we're going to do here. We're going to implement linear regression. Why linear regression? It's the simplest supervised algorithm we have. So what we do is this basically. Given some set of points, we are going to fit the most ideal line we could. And say this is our training phase, fitting this line. And in the prediction, I mean, whatever the machine is predicting, say we are asked to find what this whatever is at x equals 7. So what I would do is I would plot this point 7, 6.81. So that is what the machine would predict. Basically, this is exactly what we are going to do, except we are going to make a program do it. So here is another example here. If you see, the line of the best fit is going to be whatever your machine is going to give you. So here's the math behind it. So we are going to have a program that will take a lot of tuples of x and y, and it is going to give you two values, which are going to be the coefficients in this linear equation, this general y of x equals a naught plus a1x equation. And how we are going to do this is we are going to minimize the error. This line, like whatever this line predicts, it's going to have some kind of error from our data set. We're going to fit a line so that we minimize that error. So here is how we are going to calculate error. There are many ways to calculate error, and they might give you a different line. But here's what we are going to use. We are going to get the variance of your predicted points from the data set. How we do it? Variance squared. I mean, sorry. Variance. Sigma square is variance. Variance equals sum of square of the difference between the predicted value and the actual value squared by the total number of values. So here our variance would be
linear regression here the best suitable approximated line for it.
Yeah. Okay, actually, that's not going to calculating variance by hand because it's going to become very messy. Anyways, so that's how we are going to calculate variance, and then we are going to minimize that. To minimize that, what we are going to do is we are going to find a point on this R square space where the variance is stationary. That is, we have this partial differential equation. So what I am doing here is I'm not just minimizing variance, but n into variance, because n is just a constant. It doesn't matter. So that our calculation is going to become much easier. I will come to it. So basically, we have the partial derivative of n into variance the partial derivative of n into variance with respect to the first coefficient equals 0, and the partial partial derivative of n into variance with respect to the second coefficient also equal to 0. So this will get we'll basically get two linear equations in A0 and A1 when we do this, which we can arrange in a matrix like I've shown below. We can actually try doing this if we want. Let me see. Do we have time to actually show how this derivative is calculated?
I think, yeah, there will be time, I think. Yeah.
Okay. Do you think we'll show these people this or leave it as an exercise?
Maybe as an exercise, it will be better.
Yeah, then we leave it as okay. So I'll just give you what exactly you have to do. You'll have to take this summation, just calculate the partial derivative with respect to the two equations. You'll notice that you're getting linear equations in the two coefficients, and y1 and x1 are your data points. They're not variables, so the partial derivative of those terms with respect to these coefficients will be 0. And then you just arrange the linear equation in a matrix like I've shown below, and then you invert the matrix so that you'll get the two coefficients. That's how linear regression is done. This can also be expanded to several degrees of polynomial. The exact same procedure follows, except you'll have more coefficients and a larger matrix. So yeah, that's the theory behind linear regression. Now we'll go into implementing linear regression using scikit. So first you'll have to prepare the data. So sometimes your data is binary as in like positive and negative basically. So in that case, we will type this code so that we will take the binary data and encode it into zeros and ones. AM will basically show you everything in a Google Collaboratory, so I'm not going to go through the code right now. But whenever you need to refer to this code, you can come to this PPT. We will share it on Teams. And the next thing you do when preparing data is you receive all the data in a data frame, and then you remove all the rows that don't have entries. This is important because sometimes there are rows in CSV that do not really have a y value or an x value. That data is basically not useful. So what we will do is we will strip off all those data. And how exactly we do this? We covered this in the first session here. This is how we remove null data. We'll have to do this twice here for x and y. So, and the next thing you do when you prepare data is get x and y in NumPy arrays. How we do it is we do okay, that was covered in pandas anyways, so I'm not going into it. And then we split the data into two. We split it into training set and testing set. This is important because you have to see if your program performs just as well on a testing set before you put it into use. What that means is basically you use one set of data to train the program. So the program will find the straight line from the first set of data, and then you'll run it on a test data to see how well it performs. So you'll find either the accuracy or the error that it has in that data set or whatever. So that kind of splitting we do with this function I've shown below. So this will give you, this will basically split your two numpy arrays into 4 numpy arrays. And then we normalize the data. This is not really necessary always. We do this when our data is either really large or really small, or the range is really large, or things like that. So we run it whenever our data is, yeah, really large or really small. And then the final step, so we prepared data so far. After this, we run regression. Until here whatever we've done, it's the same for all types of regression. This is where we actually come into linear regression. So we import linear regression, and then we create a linear regression object, and then we train. And then you can generate a numpy array of predictions by giving your object an array of test data, and you can compare your predictions with your whatever your y test was. There are different ways of comparing. You could probably get the square error, or you could probably generate a confusion matrix, which we will not go into much in this summer school. Or you can find accuracy. This is not accurate, this is accuracy. So yeah, that is linear regression, and AM will take over from here.
Yeah, 1 minute. Let me see.
You're audible. It could be better if you speak up a bit.
I'm a bit louder.
Yes.
1 minute. Screen visible?
Yes.
So now we'll implement the linear regression algorithm on the basis of one of the data set. This is when this data set is in the drive. If you want, you can put this in the chat. Right? If you want to do like walk along, run along with me, like you guys can try opening a IPython notebook and try running me. Any of you trying to like run along with me? Yeah. Audible?
You're audible. Yes.
Anyone trying to run along with me or just watching? Just open Google Colab and make a notebook. Or even I'll give this link, just copy this. Make a copy of this notebook. Permission. Yeah, anyone can view. Just make a copy of this and you can edit your code and run. So I'll start off. I assume -5. So first we'll import all the packages, pandas and numpy and matplotlib. So as we did in the last session with numpy, pandas and matplotlib. Next step, we'll get the data set. This is basically a weather prediction data set. From where we'll try to compare the temperature and apparent how temperature vary with apparent temperature, and we'll plot it, and we'll train data with linear regression, and finally with the test data we'll predict the accuracy and how linearly the temperature and apparent temperature varies. So the next step, we'll just mount the drive. Like, this is one of the method to get the dataset in the Google Colab. Like, you can upload the dataset in the drive, and from using this command you can get the drive link into a Colab. Like, connect your Google Drive to the Colab, and from there you can get all the content of Google Drive using this command. Or one more way you can do is like this. Just do this and upload the data set. I'll upload it just like this. You can do. You can see this CSV file is uploading the dataset file. One you can do connect to drive and upload dataset. The problem with this way is that every time you reset your runtime, this upload gets deleted. So you have to upload every time you open this file. So this is more convenient, but one thing is that you have to give permission every time while connecting the drive. So both have their flaws. And the next way we'll upload the CSV file, which is I'm uploading, since it is also how to upload. You just do this in Colab. You go to the drive, since you uploaded the drive, and go to the file link. Just copy path and paste here. Now I have uploaded the dataset, and using the head command, you see the first 5 rows of dataset. You can see how it varies. This is how the dataset varies. You have fermented date, summary, temperature, all the stuff. So we'll compare these two columns, temperature and apparent temperature, and do a machine learning algorithm to predict apparent temperature from the temperature we have given. Using the describe command, we get all the statistical details of the dataset, like temperature, the total count of temperatures, the mean, standard deviation, minimum, maximum, etc., and this stuff. And using this command, we get all the information about the dataset. Like, you see, the temperature has 96453 null value and 0 null count. All the counts are none, and the object type is float. Similar for apparent temperature, humidity, fit, etc. Now I'll count the sum of null values using this data frame.isNull.sum. I see that what we targeted, the temperature and apparent temperature. These two values have 0 null value, so we don't need to clear anything and add up anything. Now we'll divide the data set, like our target value and independent variable. Those two will divide those columns. See, first, from the data.
What happens when there is missing value?
You just see, when there is missing value. See, you have a target value, but in your x, y and xm, you have y, the array size of y is more than of x, right? There will be a mismatch while running the algorithm. So you want to have a y for every x, right? But when there is no value, so we'll get the range of x is less and the range of y is more. So there will be one or more y's which won't have any x. So there will be a problem in execution. So you need to plot both target and independent variable as equal number. The size of both the arrays should be equal. Is it clear?
Yes, yes, okay.
So now we are splitting now we are making one more data frame. using the just split using both two columns from the our original data set, like temperature and apparent temperature. This is for row. This this thing column before comma is for row, and this before is for column. Since we're including all of the rows, we just keep it as a column. And since we are using only just extracting two columns out of the data frame, we keep temperature and apparent temperature and print the first wave elements of the data set. We can see columns are temperature and apparent temperature. Now we'll see how visualize both of them, how they're related, temperature and apparent temperature. You can see that they're nearly linear with some noise, right? So we'll basically fit a line on this, which will predict when you give a new value. Like when you give a new temperature value, it will predict the apparent temperature value from whatever is trained from this data. Right? Is it clear till now?
Yes.
You can see that we converted the data frame to an array, numpy array, using this. Using the values comment of the pandas, we just the column of the the data frame, the x column of temperature column of the data frame, we convert it to a numpy array x, which is this array, and we use same using apparent temperature column of the data frame. We convert it to an array y using the values command. Now we got our independent feature data using a numpy array and target data using this. So in the slides, as you see, get the data into we add until this, get the data into two numpy arrays for x and y. Here we got the values of x and y, right? Till now it's clear, right? Now we'll go to the fourth steps. We split the data into training and testing sets, right? So we'll model the train set split from the scikit-learn model selection, which you have here. We're importing this, and then we'll just do this command is extend equal to train test split xy test size and random shape. So you can see that this is the we put train size as 0.8 and test size as 0.2, and we'll run the command. Now one more thing, that will reshape the array. See, I think we mentioned it somewhere. Okay, so when by running the linear regression, the the extend, ytran, and all the steps require to be reshaped. I'll show you by printing. 1 minute. I'll create a new code. You see, and now you see. Will mention where is see, like if you remember this gives what this is similar to the reshape dot -1 to 1 is similar to this. Like it will initialize an empty array and gives an array which of duplet arrays. You see, the same thing does the reshape dot -1 to 1 similar. So Then we'll go to move to the next step. We'll import the linear regression module from the scikit-learn, and here the regression object, we have created the regression object as model. We click model as linear regression. Here model is our regression object. Then we'll feed the regression, the X train and Y train using the regression object, and we'll run the code. And there is something. One minute, let me give me a minute. No, I haven't run. We haven't run the previous cell to reset. And now it's fine. Now the command has run. Like we have trained the model to fit the X and Y data from our training data set. Now since we have trained the model, so we'll get the coefficient of like A0 plus A1x. So we'll print A0 and A1. The intercept is basically A0, and as in this A0 and A1. Intercept is A0 and the value of coefficient is A1, and we'll print this coefficient. I got the values. Now we'll predict the test data, whatever we have done. I got the test data. I get an accuracy. Test accuracy. This is test accuracy. What we did here, we found the coefficient and intercept, then this step, the regression object, here the regression object is model, and we found the prediction data using model.predict.xtest. This data we printed whatever we predicted the y value from the xtest. I'll show you the xtest value. 1 minute. This is text file. You can see this is the testing value. This is the prediction value. When the input is 14, the output is 13. When the input is 12, the output is 11. When the input is 23, output is 24, like this. So we give into the model, we feed it xtest, and it gives y predict as the output value. And now we're gonna using the scikit-learn features, like since our regression object is model, so we'll print the accuracy score of the model, which will be like here we are getting 0.98, which is still 98.53% accuracy we are getting. So our model is working good enough to predict the value, and here we got the accuracy of the testing values. Is this 0.9? Now we'll get a new data, like what? Let's say we're taking 8, the new data. Now I'll predict new data using the model, which is giving 6.47. If we take as new data as 10, it is giving 8.7. Now I'll get 10, 8. I'll get 12. This is giving 10.92. Like that, whatever you need data we get, we are getting the values. I'll print the values here. 7, 8, 9, 13. like this. See, for this, all this value, the prediction you're getting is this. So like our model is working finely, you can say. You have any doubt till now? Anyone? I'm open. Now I'll plot the results. So plotting, this is our training data X and Y, which are plotting by scatter, the blue thing, and our test and predict data is like our testing data is this calling by color red. I'll run the command. You can see that this is how our training data looks like, and our testing line is this straight line, which is linear. You can say that our model is almost linear. Like, so if it like pretty well fitted the like points to behave as a line, and like we found the west line with accuracy 98%, and the next we'll plot the actual data and predicted data plot. This is the apparent temperature and this is the temperature. The accurate, the first blue points are the test y test and x test data, which is the actual data. Y test is the actual data. I'll tell you what all these things are. Okay, I'll write you in a note since many of you have a problem. Alright, understanding. Here y test is actual value of target from data set. Y predict I hope this makes everything clear. I think. So here what I'm doing is in this line, first we're plotting the raw data, like whatever the actual value of the apparent temperature with respect to actual value of the temperature. That is the blue scattered points. And in the next scattered points, what we're doing is our actual value of the temperature. What we're plotting is the predicted value of the apparent temperature from our model. You can see the red ones and blue ones like almost coincide, and with some error of course, and that's how our model is working pretty fine, you can say. With accuracy 98%. I'll print mean square error. Wait. One minute. I'll import 1 minute. Error plating Y predict. Y test. So you get mean squared error as the error value as 1.68. That is quite, like, you can say it is fine, like good enough the model to work. And this is our model VF says we get that plotting of the model, and for new value it gives this prediction. Can like add more values also. I'll print mean square error for new values. Wait, will print that. Like V6, 7.2, 5.5, 8.9, like this. New period. Just make new data and make new prediction, and we'll find the mean square error of the new prediction, which is new period. Is giving value 2.3, which is not so bad from 1.68, so it's fine, I guess. And the fitting is almost linear, so the model is working fine. I think this much for this implementation. Anyone has any doubts? Jim, no doubt. I'll stop the screen sharing. I'll give it 2 minutes break. Should we start the neural network part, or I'll help them with the task?
So we'll give the tasks and answer any doubts and then keep it for the next class.
Okay.
I'll give them of the tasks right now.
Okay, fine. A neural network will do next session.
Yeah.
Okay.
So I'm sharing my screen in a bit. My screen is visible?
Yeah, it's visible.
Okay, so here are the tasks for this class, this session. Firstly, we want you to download this dataset we've linked here. And implement linear regression just the way I showed you guys right now with Scikit. And we want you to try plotting your training data just like he did against what you predict. Either that, or you can get the coefficients like he did using model dot intercept and model dot coefficient and plot it against the straight line. Either of those. Which we just want you to visually compare your results and the training set. And what we want you to submit for the first task is we want you to tell us the coefficients you get. We'll give you a G form in the WhatsApp group and Teams. We want you to submit the coefficients you get. And in the second task, it's the same data set, but we want you to use pandas and take only the values in which y is greater than 30. I mean, y as in your data set, it will be apparent temperature. Greater than 30. Implement linear regression, but this time we want you to implement it from scratch using the mathematical background I just showed you. And here are some functions you might need. You might need NumPy's matrix solving function. You might want to Google that up and figure out how to use it. And you might need NumPy's sum function, which will sum all elements in the array you give it. And here also we want you to submit two coefficients. We're going to keep deadline of all tasks to the last. So like you'll be submitting all the three practice tasks, three sets of practice tasks at the end together. And the third task, you don't need to submit this, it's a challenge task. We want you to try figuring out fitting a saturation growth equation, which is of the form y equals ax by b plus x, using the linear regression function. Do not use any other functions in scikit. Do not use logistic regression, for example. Scikit may or may not have a saturation growth regression one. I am not exactly sure, but we want you to not use it. We want you to figure out manipulating this equation to implement it using linear regression itself. And the fourth one is also a challenge task. We want you to use the mathematical background I showed you and fit a quadratic polynomial instead of a linear equation. This is also from scratch. So you might again need NumPy solve and NumPy sum. But yeah, so these are the tasks for today. And in case you were wondering if we will give you solutions for these tasks, no, we won't. We want you to figure them out. Basically, all tasks you need to submit, you have all the answers in the PPT itself. And the challenge tasks, we don't want you to submit. Plus, we want you to learn figuring it out by yourself using the internet. So we will not give you solutions for the tasks. You can ask doubts in Teams if you want. If you have any doubts, there's a channel for doubts, and we'll be glad to answer. So yeah, that's it for today. Thank you for attending and have a nice day. Bye-bye.
Thank you.
Thank you for attending. Let us go.